Welcome to iTCA, iTeachCybersecurity Academy, an online academy dedicated to making cybersecurity simple, useful, and practical for everyone. At iTCA, we break down complex technical ideas into everyday language so that anyone, regardless of background, can understand how the digital world works and how to protect it. You're currently enrolled in the Introduction to Data Communication Beginners course, and this is Module 2, Network Architectures. This module is extremely important because it forms the foundation of networking and cybersecurity. Before you can defend systems, detect attacks, or even understand hacking techniques, you must first understand how data moves and how networks are structured. Most cyber attacks don't start with advanced hacking tools. They start with network access. Attackers first ask very basic questions. Where is the data flowing? Who controls the network? And which devices are allowed to communicate with each other? If you don't understand network architecture, you're essentially trying to defend a building without knowing how many entrances it has, where they are located, or which ones are guarded. This module, and especially this lecture on network architectures, solves that problem by helping you understand how networks are designed, how devices communicate, and how security risks change based on those designs. This lesson is designed for absolute beginners, aspiring cybersecurity professionals, IT students, and anyone who wants to understand how real-world networks are structured and secured. Let's now focus deeply on network architectures, because architecture defines how data communication happens and where cybersecurity controls must be placed. Once you understand network types and design models, cybersecurity concepts will start to feel logical instead of overwhelming. We'll begin with the 3 major network types you'll encounter in the real world. A local area network, commonly called a LAN, connects devices within a small geographic area, such as a home, office, school, or small organization. In most cases, all devices on a LAN are owned and managed by the same entity. From a cybersecurity perspective, LANs are easier to secure because devices are physically close, access can be tightly controlled, and traffic patterns are usually predictable. However, a LAN is not automatically secure. Insider threats, infected USB devices, and weak internal passwords can still compromise the entire network. If just one device becomes infected inside a LAN, malware can spread rapidly to other connected systems. A metropolitan area network, or MAN, covers a much larger area such as a city, large campus, or organization spread across multiple locations. MANs are usually created by connecting multiple LANs together. As a result, cybersecurity becomes more complex, data travels longer distances, infrastructure may be shared, and the number of access points increases. Attackers often target MANs by exploiting weak links between connected networks. To secure a MAN, organizations must implement network segmentation, encryption, centralized monitoring, and strong access controls across all locations. A wide area network, known as a WAN, spans countries or even continents. The Internet is the largest and most familiar example of a WAN. WANs rely heavily on third-party infrastructure, such as internet service providers, undersea cables, and satellite links. From a cybersecurity standpoint, WANs are the most exposed and most targeted networks. Data often passes through untrusted environments. Interception risks are high, and encryption becomes absolutely mandatory. This is why technologies like VPNs, TLS, and secure routing protocols exist, to protect data as it moves across wide and uncontrolled networks. As networks expand from LAN to MAN to WAN, security complexity increases. LANs emphasize speed and control. MANs balance scale and manageability. And WANs prioritize reach and resilience. At every stage, stronger security controls are required. Now that we understand when networks operate, let's look at how devices interact within those networks. In a client-server architecture, one central system, the server, provides services, data, or resources, while other devices, known as clients, request access. Common examples include web servers hosting websites, email servers managing communication, and authentication servers handling user logins. From a cybersecurity perspective, client-server models offer centralized control, easier monitoring, and stronger access management. However, they also introduce a major risk: a single point of failure. If attackers successfully compromise the server, they may gain access to many connected clients. This is why servers are protected with firewalls, intrusion detection systems, strict authentication rules, and continuous monitoring. In a peer-to-peer architecture, every device acts as both a client and a server. Devices communicate and share resources directly without relying on a central authority. Examples include file-sharing systems, some messaging platforms, and blockchain-based networks. From a cybersecurity standpoint, peer-to-peer systems have no single point of failure, but they are much harder to monitor and control. Trust is distributed, and attackers can exploit weak devices to spread malware across the network. This makes strong endpoint security, encryption, and identity verification absolutely critical in P2P environments. In comparison, client-server architectures are easier to manage and secure, which makes them ideal for enterprises. Peer-to-peer architectures are more resilient, but riskier when poorly managed. Cybersecurity professionals must always identify which model is in use before designing defenses. Let's now compare wired and wireless networks, focusing on their security implications. Wired networks use physical cables to transmit data. This provides stable connections, faster speeds, and a degree of physical access control. However, physical access does not mean zero risk. Attackers can still tap cables, compromise switch ports, or exploit poorly secured network closets. Wireless networks, on the other hand, transmit data using radio waves. This offers flexibility, mobility, and ease of deployment, but it significantly increases security risks. Wireless signals can be intercepted, rogue access points can be created, and weak encryption can expose sensitive data. This is why modern wireless security protocols like WPR3 are essential to protect data in transit. Network topology describes how devices are arranged and connected. In a bus topology, all devices share a single communication line. If that line fails or is compromised, the entire network is affected. While simple, this topology is insecure and largely outdated. In a star topology, all devices connect to a central device such as a switch. This improves monitoring and fault isolation, but it also means the central device must be heavily secured. A ring topology connects devices in a circular pattern where data flows in one direction. This simplifies traffic flow, but creates vulnerability if one device fails. A mesh topology connects devices to multiple others, providing redundancy and resilience. This makes it suitable for military and critical infrastructure networks, but it requires strong authentication and access controls to prevent unauthorized connections. From a cybersecurity perspective, star and mesh topologies are preferred in modern secure networks because they support better monitoring, segmentation, and resilience. Poorly designed topologies dramatically increase the attack surface. Transmission media: how data physically travels. Now let's answer a simple but critical question. When you send a message, stream a video, or log into a secure system, how does that data actually move? Data travels through transmission media, and understanding these paths is essential for cybersecurity. Transmission media are divided into guided and unguided types. Guided media use physical cables. Twisted pair cables, the most common type, are affordable and easy to install, but vulnerable to interference and physical tapping if access is not controlled. Coaxial cables offer better shielding, but can still be compromised in shared environments. Fiber optic cables transmit data as light, making them extremely fast and very difficult to tap, which is why they are used in military, financial, and critical infrastructure networks. Unguided media transmit data wirelessly. Radio waves used in Wi-Fi and mobile networks offer convenience, but can be intercepted if encryption is weak. Microwave transmission supports point-to-point communication, but requires strict alignment security. Satellite communication enables global connectivity, but introduces challenges such as latency, interception risks, and dependence on third-party infrastructure. Strong encryption is mandatory. Each transmission medium has trade-offs. Guided media offer stability and control, while unguided media offer flexibility and reach, but expand the attack surface. Cybersecurity professionals must understand these differences to apply the right defenses. In this lesson, you learned how LANs, MANs, and WANs differ, and how security risks scale with size. You explored client-server and peer-to-peer architectures, compared wired and wireless networks, and understood how network topologies influence security design. You also learned how data physically travels through guided and unguided transmission media. You now understand one critical truth: network architecture directly shapes cybersecurity strategy. In the next lesson, we'll dive deeper into transmission media and examine how attackers intercept data and how defenders stop them. Continue to the next lecture. Take your time with these concepts and always remember, strong cybersecurity starts with understanding how networks are built. Welcome to iTCA, where cybersecurity finally makes sense.